So in contrast to the power cycles we talked about previously, so the Carnot cycle or the Rankine cycle, what we're going to talk about now is the refrigeration cycle, which has the opposite goal of those power cycles. So refrigeration has opposite goal of a power cycle. Right? And so what we do here is, rather than adding heat to produce work, what we do is we add work to the system to remove heat from something. Okay? Right? And essentially is the fluid or the refrigerant in the system passes through an evaporator, which receives heat from the object that you want to cool. Needs to be cooled. So one probably important application of this is the refrigerator in your home, which you use to cool down your food. Okay. All right, and so the way that a common refrigeration cycle works is it involves 4 unit operations. So it involves an evaporator, like I've already mentioned. It involves a compressor. It involves a condenser. And it involves a throttle valve. Okay. All right, and so with the refrigeration cycle, what we have is stream 1. We have some sort of liquid, right, that goes through an evaporator, and then it receives QH from the object that you want to cool. Okay, so it receives this QH, and it causes the it causes the fluid to then evaporate. So here, start with liquid, and then stream 2, you now have a vapor. Okay. This vapor then goes through a compressor, which increases the pressure of that vapor in stream 3. And in order to increase the pressure, work from the compressor is added onto that vapor. Okay? And it's done in such a way that it's isentropic. Right? So it's an adiabatic compression. There's no heat that's involved. Alright, so this vapor then, after it comes out of the compressor, it then goes into a condenser, which turns it from a vapor back into a liquid. Okay? And during this condensation process, heat is removed from the refrigerant, and this is done in an isobaric manner, so the pressure does not change. Alright, and then this liquid then goes through a valve, a throttle valve, which just reduces the pressure of that liquid even more. Okay, so as it passes through the valve, there's no work, there's no heat, and so the throttle process here is isenthalpic. Okay, and so in the refrigeration cycle, we use some sort of chemical refrigerant as the liquid and vapor that passes through the cycle. Okay, and so throughout history, there have been many different type of refrigerants that have been used. Refrigerant fluids. Okay, and so for example, up until the 1990s, a very common type of refrigerant that was used was this carbon chlorine 2 fluorine 2 chemical, also known as Freon 12. Okay, and so this one was very popular prior to the 1990s. Okay, but then in the 1990s, that's when people started, understanding or getting an idea of, climate change on our planet, and they realized that society's use of Freon 12 was actually pretty bad. Um, and Freon 12 actually ended up getting banned, and the reason for that is that when Freon 12 goes into the ozone layer, it reacts with sunlight and radicals in that ozone layer, and can actually cause degradation of the ozone layer in our planet. Right? And this degradation is due to the fact that Freon 12 serves as a source of chlorine radicals. Right? I won't go into the chemistry of it, but essentially that's the reason why Freon 12 was banned. It forms these chlorine radicals in our upper atmosphere. Okay. And so since the early 1990s, there's been a lot of efforts to develop more environmentally friendly sort of refrigerants. Right? And so some more environmentally friendly ones are hydrofluorocarbons, which you see as abbreviated as HFC, or hydrochlorofluorocarbons, which are, both of these things are more environmentally friendly alternatives than Freon 12. And typically you'll see these HFC and HCFCs named as like Freon 22 or just some other number. And so these higher number Freons, they're supposed to be better for the environment. Though they're not perfect, they could still cause some degradation of the ozone layer, but it's not as bad as Freon 12 was. Okay? And so in any case, there are a lot of different types of refrigerants out there. And so when you're doing this sort of refrigeration cycle analysis, you can actually look up the thermodynamic properties of these refrigerants in various plots. So refrigerant properties are typically read from plots. Okay? And so one example is we could look at the HCFC called Freon 22. Right? And so here's an example of the plot for Freon 22. And so in this plot, it's a very busy plot, I admit. But essentially the y-axis here is absolute pressure. The x-axis is the specific enthalpy of the refrigerant. And then in the middle, there's a lot of details, but some main ones I'll point out is the lines that go this way, that's the specific entropy of the refrigerant. And the lines that go this way, this is the specific volume of the refrigerant. Okay? And so in these plots, essentially, if you're doing your thermodynamic analysis of a refrigeration cycle, if you know two parameters, so let's say you knew the absolute pressure and the specific enthalpy, what you could do is take the intersection of those two properties, and then from that intersection, that would give you, for example, the specific entropy, or it's the specific volume. Okay? And so the way to use these plots, they're similar to the Mollier diagrams, is if you could figure out two properties, that allows you to get a third one from the plot. Okay? And so we'll get practice in how to use these plots when we work through the example problems in class. The last thing I want to say about the refrigeration cycle real quick is that if you want to quantify the performance of your refrigerator or your air conditioner, rather than talking about an efficiency, with refrigeration, instead we talk about something called the coefficient of performance. Okay. All right, and so this coefficient of performance, which is abbreviated as epsilon, and I'll just put COP here. The way to think about it is it's a ratio of what you want over what you pay. Okay. And so with a refrigeration cycle, what we want is we want to remove heat from our food or some object at a specific heat rate. So what we want is QH. And what we pay is the work that we need to put into the compressor. Okay? So the coefficient of performance would be what our QH is over the WC. And the value for this coefficient of performance is greater than 1.